last time we left out, it was question 7. Let's go to question 8 now. So let gamma be a regular plane curve and let lambda be a constant. The parallel curve gamma power lambda. Now, okay, they're saying gamma power lambda, it should just be like gamma subscript lambda, as in it's a completely new curve. So it's defined by this thing. It's gamma of t plus lambda n sub s of t. Show that, right, so this is a parallel curve of gamma, right? Mm-hmm. So, okay, what's a parallel curve? I mean, they're defining it like that. Okay, what is ns of t? Well, we don't know. N sub s. Oh, so that's like the normal vector of gamma, right? So this is your gamma, um, tangent vector, your normal vector, whatever. And so you're saying lambda ns of t. So it's something like this. Oh, so it's like it's this vector. Okay, so this ns is not going to be the same thing at all points. Like over here, it would be something like this. So we just have that as the thing. So that's kind of weird. But okay, sure. So it's in a way parallel, but not really. But well, whatever. So it's some curve, which is this is extremely weird. But yeah, so you just define this new gamma lambda thing. Okay, what do we want to show? So show that if k, so kappa s of t lambda is less than 1 for all values of t, then this thing is a regular curve. Find its sign convention. So when would this be a regular curve? This is a regular curve when this guy's velocity is never 0. So it's velocity which is like v power lambda. So I'm gonna call it that. That's equal to, so the velocity of gamma, so v of t, plus, so lambda, and then this is n sub s of t, the derivative of that, right? Okay, so yeah, we want to sort of make this slightly different, don't we? So we just want to show that this guy is never like 0, right? And we know that gamma is a regular curve. Cool. So v is in the direction of t, so it's something like a times of t, and this n dash of so ns dash, so better it's a plane curve. It's a plane curve which is like the curve, the torsion is 0. So then that means this thing would also be something in the direction of t, right? Yeah, so it's something like b times of t. Yeah, that actually makes sense. Sure. So what is dn by dt? I mean, it's the question. Not dt, d small t. That's what we're looking for, right? Uh, so yeah, okay, that's where the kappa thing is going to come in. That makes sense, because kappa was defined as just t dot upon, so the magnitude of that upon velocity, right? Yeah. So if you want to get this thing somehow, well, what is this? So n is in fact just, so you're gonna have a kappa over there, don't you? Right, so just derivative of 1 upon kappa, times what, times heck, I'm kind of forgetting this stuff now. So times the t dot thing. Yeah, so just normalize that, right? So to normalize it, it has to be, oh, so it's supposed to be kappa times v. I kind of keep forgetting that, whereas t dot is in fact defined as kappa times of v. Sure. So it's this stuff. Okay, so this would just turn out to be t double dot upon kappa v, and then plus t dot, and then the derivative of this is like d by dt 1 upon kappa v. So these are just scalars. This will be some sort of a scalar. T dot is in the direction of n, and t double dot is in the direction of t, right? Yeah. So okay, so we got t double dot over there. This thing is, and so lambda times of that. I guess so, that actually makes sense. So just lambda times of this, lambda times of that, and that plus v of t. So what I should be saying is something like vt plus this stuff. Yeah, that seems okay. Now the thing is, t double dot, what is the direction of that? That's a hard one to tackle, isn't it? Yeah, right, that's a hard one to tackle. So So both of these are one component, and this is in some other component, right? So we want to show that this will be regular for all values of t, right? So these are both functions of t, by the way. Okay, cool. Such that, so this lambda k sub s of t, so what, oh, I see, because this thing, it might actually be 0, right? Yeah, so not just, okay, fine. So this thing might be 0, this thing might be 0, right? Sure. This thing is never going to be 0. What about this one? Hey, so you're saying t double dot, something is fishy about this? Yeah, it is. Okay, come on, think about it. Yeah, you probably just have to write t double dot as a function. So what you have is like t double dot is just equal to, what is t, right? Actually, what's t dot is the better thing to ask. This is so confusing. Right, so we want to show that. I'm also going to find the sign curvature of this thing. In the end, you just want to find the sign curvature. Right, it's a regular curve. The derivative of that, right? So it's just supposed to be like, so lambda is a constant. Yeah, this isn't actually making sense, is it? No, it's not. So this is in the direction of negative t most likely, but still, what is it exactly? Hey, so what's kappa times of v? That's just the magnitude of t dot, isn't it? Sure, but what's the magnitude of t dot? Oh, that does change actually. It's not like that won't change. It certainly will. dn by dt is equal to d by dt. Yeah, that's okay. T double dot upon kappa v. Yes, that's fine. Why is it that I'm unable to make any further advancements? I just try doing everything using R and that stuff, so that it's like easier. Basically, what we want to show is that this stuff will never be 0. How? That's the question. Could you be writing p double dot as some sort of a, I don't know if that's still possible. Let's try to write down. So t dot, v is also a function of t, sure. But anyways, what's t dot? So t dot is just, well, the velocity vector, so it's just like r dot that upon v. So then t, sorry, that's not t double dot, that's just t, sure. So then t dot would just be like r double dot upon v, minus, so okay, plus r dot, and then the derivative of 1 upon v, sure. Then t double dot, that would just be like r triple dot upon v. Now this isn't helping, is it? No, it's not. We know that t dot is in the direction of the normal vector. Hey, so this isn't quite helpful. We need to have some sort of other way to be doing this. So if this is regular, then if lambda kappa s t is less than 1 for all values of t, then this is a regular curve. Well, what happens if it's less than 1? Then this quantity is bigger than 1. Yeah, lambda kappa of s, that doesn't make sense. t dot is that stuff, so it's just the derivative of that. That doesn't even make sense, does it? No, it does not. Lambda kappa v. No, I don't see where this is coming from. N sub s, which is just supposed to be 1 by kappa. That terms of v, obviously, kappa sub s, right? That's what we use it. So yeah, this is bad. The derivative of that. That's what n sub s has to be the normal vector. That's what I'm thinking. So then this is just the derivative of this stuff. Sure. This is getting insanely hard to deal with now. You need some sort of a vector identity to be able to do this thing. So what I remember was like the magnitude of, no, that's not a good identity to deal with. You know, a better way to be doing this is just to be sort of, you know, how do I say this? Yeah, you could be doing that. So let's try doing it like that. Let's just say that your r is more like, so your gamma in fact is more like r e power I theta, because it's all plane curves in any case. So then your gamma dot, that would be something like r dot e power I theta plus plus what? Plus I r e power I theta. Sure. What we want is the tangent vector. So the tangent vector is just like gamma dot upon the magnitude of gamma dot and all that stuff. So it will be like r dot plus I r times e power I theta upon the magnitude. That e power I theta doesn't really matter. It's just like square root of r dot square plus r square, it seems. Right? I hope that's correct. Oh no, so you also have to have a theta dot. So yeah, it's r squared and theta dot square. Okay, so that's what t is. Now everything should be doable, because now we want like n. So n is just t dot, means it's collinear to that essentially. Or since you already know what the tangent vector is like, you can just rotate this to get that. Yeah. Still, taking a derivative of this whole thing might actually be easier. Who am I kidding? I can just rotate this stuff, right? So this is a unit tangent vector. Rotating it by 90 degrees, that's just only like. So which way though? Clockwise or anti-clockwise? It's a good question. I have no idea. So for sine curvature, what happens is like whatever t is, so the angle that you're making with x-axis, you just try to increment that, right? So okay, so your curvature would be defined in that case. But what about the normal vector? Well, we can always choose the one which is like being rotated by anti-clockwise, even if that one is like down. Sure. No, this isn't a good way to be doing it. Okay, it really just depends on the curvature, it seems. So just figure out the curvature. So what's psi? Psi, it's going to be like theta plus the tan inverse of, so this is all just magnitude, it doesn't really matter. It's a have to have theta dot. It's tan inverse of r theta dot upon r dot. Sure. So you want d psi upon ds, or for our case just dt. That will make sense. So this is just, yeah, because ds by dt is like some positive quantity. So just like theta dot plus, so it's tan inverse of this. It's just 1 upon square root. Sure. So 1 upon 1 plus. Yeah, that's the way we do it, right? Yes. 1 plus this stuff squared. So just r theta dot on r dot, all of that squared, and then the derivative of that. Okay. Wow, this is really bad. So just what the, this is really not good. Gotta find the sine curvature. That's what we are finding. Sure. So it's just r. This isn't going to help. This just isn't going to help, it seems. We have to do it. So it's just r dot theta dot. Okay, so that cancels with that. It just gives us theta dot, okay, plus r upon r dot theta double dot. Okay, cool. Plus, so if I differentiate this, I just I can do minus over here. So minus r upon r dot squared, then you got theta dot, and then you got an r double dot, right? Interesting. Yeah, okay. So that's your d psi by dt. How does this even help? I don't know. But what's the direction of this? Okay, this also doesn't help. Like, yeah, it doesn't really help. It just doesn't. It's nothing I can get up of it. That was nice while we were doing the planar thing, but no, it's not helping anymore. So we're back to this stuff. What we want to show is that if lambda ks is less than 1 for values of t, then this thing is a regular curve. How about I like try to unit parameterize the whole thing? Yeah, that's one way I could be doing it. So the tangent vector and the normal vectors remain the same. It's the same direction regardless. So yeah, that might be a good thing to do. So yeah, because if this is a regular curve, the unit parameterization would also be a regular curve or something like that. Sure. So you can just rewrite the whole thing as, so whatever responds to t, you have some arc length corresponding to it, right? So just have gamma s plus lambda n sub s of s. So this actually simplifies a lot of things, because now n sub s is essentially so just t dot upon magnitude of t dot. But what's t dot? It's just the same thing as gamma dot, right? So then this just boils down to something like gamma dot s upon the magnitude of gamma dot s. But what is the magnitude of gamma dot s? Right, that's, oh wait, t is that, so this would be, this would be gamma double dot, right? Gamma double dot s, sure, because the magnitude of gamma dot s is like 1. Okay, so that is equal to your gamma lambda s at this point, right? So that's the reparameterization. And the s thing we are like using is the arc length of the original thing, right? So now we want to show that this is a regular curve. So take this guy's derivative. So just have gamma dot of s, some sort of unit vector, plus this guy's derivative with respect to s. So it would just be like this lambda gamma triple dot s for the magnitude of gamma dot s, sure. And then you got plus lambda gamma double dot s, the derivative of the magnitude, right? Now I don't know about this stuff. This is like some sort of scalar. So gamma double dot might actually be 0. There's no restriction on that, is there? No. Well, what's kappa? Kappa is just defined to be dt upon ds, right? The magnitude of that. So t is just gamma dot. So this just happens to be like gamma double dot, the magnitude of that. Yeah. I guess so. I guess that actually makes sense, huh? Yeah, right. So then this stuff, you can think of it as like kappa actually. Sure. This might actually be 0. That might be 0. We don't really care. So this stuff is I see where we're going with this. The derivative of gamma double dot inverse, sure. You got a gamma triple dot essentially over there. Interesting. So we can just rewrite this whole thing, can't we? Yeah, but okay, that is a magnitude, so it's still in the end just going to be like that. Just the square of that and then the derivative of that thing is in some sort of a scalar. So these two are collinear and this one is not. Now if we think about the magnitude of this stuff, it's something like d by dt of this thing, and that times of the magnitude of this stuff, right? Have I seen this before? Maybe, because in fact I have, right? This is exactly the same thing as 1 upon kappa, right? Huh. But that, okay, it's a derivative of that. That isn't something I can be dealing with. So this won't prove anything. Like even if you, so this is that times of lambda kappa. That that's the magnitude. But yeah, even if lambda kappa is bigger than 1 or less than 1, we don't really care because this could be 0. It doesn't really matter. Okay. What about this one? This is gamma dot and all that. So gamma triple dot, the magnitude of that stuff. Can you write it? I don't know. That's a problem. I have no idea. That's a unit vector. So you know that the magnitude of gamma dot is just going to be equal to 1 all the time. So square that. So this is like you are taking the dot product. So what does that mean? That just means like gamma double dot is perpendicular to gamma dot. Sure, which is like a well-known thing. So what about gamma triple dot? Hey, so this is actually doable. So what about this? Gamma double dot, gamma dot, that's equal to 0, right? The dot product. So now taking a derivative of that, you would still be having just 0, right? So just like gamma triple dot, dot product with gamma dot, right? Plus gamma double dot, dot product with gamma double dot. That's going to be equal to 0. So this thing is like just, oh, so gamma triple dot dot gamma dot, that's actually equal to negative of gamma double dot squared, which is very nice because we know this is a unit vector, right? Okay. I see what's going on, and we know that both of these things, gamma triple dot and yeah, both of these are in the same direction because so gamma double dot is perpendicular to gamma dot and gamma triple dot is, it's not actually perpendicular to gamma double dot. That's not how it is, right? Okay, cool. So we know for sure this thing is not in this guy's direction, but another thing is that the component of gamma triple dot in the direction of gamma dot, that is this stuff. So if I had to take the first component, right? So when I say the first, I mean the component along gamma dot. That component would, and the other one would be perpendicular to it. So that would just be like gamma dot is like 1. So 1 in the magnitude wise plus this is the thing, right? So just, yeah, sure, it's the square of that. So it's just minus lambda right, which is what? It's just kappa. Yeah, okay, that actually makes sense. So if lambda kappa is less than 1 all the time, well, we are done because then this thing can never be 0. And if that's never 0, at least one component is never 0. So your vector is always non-zero. Sure. So then it's a regular curve. Also find the sine curvature. The curvature is just like gamma double dot. Okay. That's a weird question. What do you mean find its sine curvature? Signed curvature. We could have done the exact same thing you're doing with the complex number stuff. Yeah. I don't think that's a good idea. So t dot is in some direction, we want to find the angle, right? So the derivative of t dot with respect to t, it's not that which we are looking for. We're looking for, hey, so the curvature doesn't really matter, right? I mean, like the parameterization doesn't really matter. So essentially what we're looking for is if you parameterize it using the arc length, right? Hey, this is very weird. So if you parameterize the whole thing using the arc length of gamma, right? Then you would just be having like gamma lambda t is equal to, sure, because that was okay, right? It was just velocity. That makes sense. Yeah, okay, so that is equal to gamma, so just the arc length over there. Hmm. Wanna figure out a tangent vector first? Sure. So m of s plus lambda. So the tangent vector will be the same thing as what we were doing before. So it's s over there. That would just be the same thing as gamma double dot upon the magnitude of gamma double dot. Right. So your gamma lambda, the derivative of that is to s. That would be just this quantity gamma dot plus the derivative of that, right? Okay, that was as before, sure. And then what we want to do is figure out the angle that this vector makes with the x-axis. How? Uh, Good question. Mm. So gamma dot is where this was going. So your plane curve is something like that. So I bet your normal does change, right? So that also causes stuff to happen. Yeah. Uh, sure. So this is supposed to be going like that, but we know that the normal will change at different points. So because of that also you will be having a bit of a difference, right? It depends on lambda and all that. Okay. How do you find the direction? So gamma dot is in this direction and then ns somewhere in this direction, and so you want a particular angle. This might be some in crazy direction, we don't really know. And this is your psi, right? So the one with x-axis, how would you define that? You can find the angle that this makes. Yes, yes, you can do that. So you can, hey, so if you, okay, that's a bad idea maybe. What I was thinking was if you reparameter, so if you write this thing, if you write as this as something like a times of gamma dot plus b times of ns, right? In that case we might just be able to figure stuff out, figure some stuff out. mm. Circular curve and all that. Sure. Are we sure this thing is gonna go upwards? We don't know, because okay, so this would be just some angle it's making, and based on that curvature you can kind of define that. And ns, well, it's either upwards or backwards. How do you figure out the sign of that? You don't. That's the problem. You don't know how to figure out that sign. It's completely based on these things. Find it sign. I don't know what you are talking about. Like, it's not like I just give you something like some value. I seriously don't know what you're talking about. Just gonna move on. Like if you gave me some options or something, maybe I would have been able to like understand what's going on, but no, I just don't get it. So I did show that, and I am going to move on now. Question number 9. I mean, just calculate this for God's sake, and then just find the curvature itself, right? So not a big deal. A unit speed plane curve has a property that its tangent makes a fixed angle theta with gamma s for all s. Okay. Wait, with gamma s. So gamma s is like, so this is, let's say, your origin. You have this as a thing. This is your gamma s, and it makes a fixed angle theta, right? This is your tangent vector, right? Oh, so this is like where complex numbers come in. So basically, you just have let's say that z equal to r e power I theta is your, or just say gamma. Let's choose gamma actually. Gamma equal to r e power I theta, that is your parameterization. I shouldn't be using theta over there. Just use phi probably. Yeah. So r is a function of s, phi is a function of s. Yeah. Now, what I was going to say was, right. So it's a unit speed stuff, isn't it? It's just got gamma dot that's equal. So its magnitude is 1, and this would just be like e power I phi plus theta. Yes. Show that first is that if theta equal to 0, gamma is a part of straight line, theta equal to pi by 2. So basically based on theta you want to figure out what curve you are getting. Okay, I see. Logarithm is pi. So basically just solve this equation, right? I see. Interesting. So we know that gamma dot is just basically equal to r dot e power I phi plus r dot phi dot iota e power I phi, right? So what you're essentially saying is that e power I theta, that's equal to r dot plus it's not r dot over there, sorry, plus r, so r phi dot I, right? Yeah. Okay, so you're saying that r dot is just equal to cosine of theta, and then so that's a constant, by the way. This whole thing is in fact a constant. Why am I even thinking about it all that much? Okay, so you can just integrate it right away. Integrate with it to what, by the way? I don't know. Well, so r can be thought of as a function of this is crazy, isn't it? Yeah. So r dot is a constant quantity throughout, it seems. Yeah. So you can just say that r will be just cosine of theta, cosine of theta. So just like cosine of theta times s, right? And then putting that in, it just got like sine theta equal to cosine of theta times s times phi dot. So that just means like tan theta, which is a constant, and then s inverse, that's equal to phi dot. So integrating that, just have phi dot equal to tan theta, and then you got natural log of s plus some constant, whatever, right? So it's something like cosine of theta, right? That's r, and then e power iota this stuff, so s times cosine of theta. Sorry, natural log of s plus some constant. We don't know what the constant is though. Similarly for r, we actually don't know what the constant is, it seems, right? Oh, this was r dot, sorry for that. Okay, no wait, this is actually right. It's just cosine of s plus c1, that's the problem. So it's supposed to be this stuff plus some c1, or let's just call that s0, or r0, that's better. Sure, that makes sense. I shouldn't even say 0, but rather actually, yeah, so whenever s is going to be 0, this is the thing. This as well, I should just think of it as like when s is going to be equal to 0, you will have some, okay, when s is 0 you will have some very explosion like scenario. It's not a good thing. Phi dot s inverse. Anyway, so what do we have? If theta equal to 0, then your tan theta is just so this whole term is not there anymore, and so it just becomes some plus c, so it's some direction. Then you got s cosine theta plus r naught, which is exactly just a straight line, in that direction, right? So it's a straight line, sure. If it's pi by 2, then your tan theta would be uh, so cosine is going to be exploding, so it's plus minus infinity. Oh, that's weird. And that times of natural of s, well, cosine theta would be 0 first thing, so that will cancel itself out. Hey, so if your cosine theta is 0, then it just becomes like, that's kind of weird. Tan theta, so theta equal to pi by 2, then e power I pi by 2, that's iota. So r dot is 0, and so is your phi dot. What the? No, that doesn't even make sense. No, okay, that's not 0 actually. So in that case, we just have like iota, right? So r dot is 0, so r is a constant, so you're like r phi dot equal to 1 essentially, right? So it just becomes like phi dot equal to 1 by r, so phi is just equal to some s by r thing, and that plus some sort of constant, which is a circle. So yeah, and then if that's not the case, if it's not like an extreme thing, in that case gamma is a logarithmic spiral given by this. So yes, it is. I mean, so this is basically like e power t plus e power t times e power iota t, right? Mm-hmm. Sure. Okay, so what about the r naught thing? Shouldn't that also matter? I get what you're going for, but so could I just like delete these constants completely? Is that a wise thing to be doing? I don't know. Hey, this doesn't make sense. E power I tan theta times this stuff. Okay. What the hell? The complex number we're dealing with is like that. So what you're saying is you set t to be equal to tan theta times natural log of s. Okay. So then s would just be e power t upon tan theta. Putting that in there, it just becomes cosine theta times e power t upon. I guess this is not a way to be doing it. Theta is just some arbitrary value. Right, so cosine theta of s plus c. Sure, it's s inverse, so it's certainly just that. Just see. Okay. Think about it. Tan theta could be any single, like it could be just anything, right? Okay, okay, think about it. I just got e power t. That would be e power t. Sure. Something is not right about this. It's cosine theta of times of s plus c1. That is the thing. Yes. Why this equation that it's supposed to be e power t cosine of t, and it's not necessarily this, right? Yeah, it is certainly not necessarily this. The iota part. Ah, this is so goddamn complicated. Let's take a natural log of the whole thing out there. What about the plus r naught thing? No, no, no. That does not make sense. Why would they be the same thing as that? It's iota part over there. And this thing is the e power part. Ah. What the hell? Tan theta s inverse equal to phi dot equal to tan equal to log of s plus this thing. So setting your, so it's not phi dot, it's phi over here. So setting your angle to be just t, right? So you want to write everything in terms of phi. So setting t equal to phi essentially, right? That's why t is just tan the natural law of s plus some constant. So since it's like parameterization, in any case, I might as well just remove that constant. Doesn't really matter. The r naught does matter actually. So logarithmic spiral given this. This is not the case. That's the problem. This isn't the case. It's not e power t. It could be anything. It could be just something slightly more than that. You do not necessarily have that. No, it does not make sense. Huh? R5, what the? Integrate that. Yes, that's a natural log of s plus some sort of constant. So that's the thing. S is just this quantity, so it gotta be like that. T by tan theta. Right, that is cosine theta, and then plus r naught. I'm gonna keep that r naught, not going to let it go. And then you got e power I t. Sure, that's the way it should be. So this is the magnitude, right? It's not e power t, right? E power t could be one of the possibilities. In fact, it's something different. It's e power t upon tan theta. So when tan theta would be 1, so so only for theta equal to pi by 4 does this actually make sense. So C is just wrong. What they are giving us is just a wrong thing. Instead, this is the correct thing actually. So for C, this would be the correct thing. Okay, question number 9. So question number 10, sorry. Question 10 is show that applying a reflection in straight line to a plane curve changes the sign of its sign curvature. Reflection in straight line to a plane curve. So you have some curve, whatever. You have some line, you apply a reflection to that. What you're saying is it changes the sign of its sign curvature. Yes, it does, obviously. It's kind of obvious, right? Like if this was increasing initially, this over here would be decreasing. Yeah. So how do you do a reflection around a line? Let's just say your line is parameterized as something like r naught plus lambda times of t, and your curve is like at any point, we don't really care. So like what you do, the reflection will be something like, so you get r minus r naught, so lambda times, so let's just say lambda is like a unit vector, right? Okay, so you take the dot product of that with lambda, that gives you the component in that direction. So this times of lambda once again, right? Yeah, so subtract that and you reverse that, and then you do that. Okay, so it's just 2 times of this minus r. That's the thing. That's your new vector. So if you had to take the derivative of this stuff, so if you just had dr upon ds as the initial like derivative, over here the thing is, well, let's call this thing as r dash, not r dash, let's call this as r1. So dr1 upon ds, because the arc length is the same, it's just a reflection, the arc length doesn't really change. So what's that going to be? So with bilinearity, what we have is like this would just be 2 times r dot, and it's not it, r dot lambda, and then lambda minus r dot. Yeah. Oh, that is to say your tangent also got reflected, right? Yeah. Yeah, right. So your tangent also got reflected. Sure, that's fine. What we are interested in is the angles, right? Yeah. Yeah, I want to prove that. increasing, so it's supposed to be decreasing angle. It's a unit vector in any case, right? So suppose your r dot is something like e power, so if you're, yeah, so that tangent vector is like e power I phi, right? Then you know your, so what we want is like d phi by ds, right? So what's gonna happen is like you just take a derivative of this thing, so um, I e power I phi dot, that's r double dot, right? R1 dot is something like that once again. So what you do is, yeah, right, okay, so how do you find phi? Phi dot is just equal to r double dot upon iota r dot. That gives you the sign. Sure. So this is actually going to give you this sign curvature. This is very bizarre, but that's just how it is. So we know this one is going to be like normal to it and all that, right? Fuck. So these have to be the same directions. I don't know. This is just weird. Let's just try to do it. So you got r1 dot as this thing. So what about r1 double dot? That would just be, once again using bilinearity, it's just the r dot which is changing. So it's just 2r double dot lambda minus r double dot, right? Yeah. So what is that saying? That's saying that r double dot also has been reflected. This is just gonna keep going like that. Like all of these derivatives have been reflected, right? Sure. So what we are interested in finding is r double dot 1 upon r dot 1. So an iota over there. And you can certainly be putting stuff like that over there, right? So just like 2r dot lambda minus r dot, and now we can just plug in the other stuff. So this just becomes like 2i, so we're gonna take the e power I psi thing outside of everything, so this just becomes e power, but we want to take a dot product. Shit. Yeah, you can't just really take a dot product unless you do that, right? As if you rotate, this thing changes. Eek. So yeah, but the thing is the vector does not really change, right? But it changes actually. It's like 90-degree change. So this was like cosine theta initially, now it would be like sine theta. Let's just say that lambda is like going in the direction of theta, so it would just be, so you have a psi over there and a theta over there. The angle is just like sine minus theta, so cosine of that. So yeah, but now it's an iota, so it's plus pi by 2. So it's like cosine of that plus pi by 2, which is to say negative sine theta. But that times of psi dot, okay, and that times of lambda minus dot, so it's just e power I theta minus r double dot, once again is like I e power I theta psi dot. You can just take the psi dot outside, in fact. This stuff. You don't have those things anymore. Okay. So just iota e power I psi. Sure, that's okay. And this stuff upon this new thing. So that's precisely just 2 times of cosine theta. And lambda is just like e power I theta minus power. So iota. Iota is not there actually. So just it's e power I psi. So that's your curvature. So it's like this. Right. But you also gotta divide by an iota, it seems. So I kind of forgot that. Okay, so putting that iota, what do we get? It's something like psi dot. So we just want, hey, so we don't really want that. Okay, never mind. So psi dot on iota, or you could just multiply this thing by the iota. So psi dot multiply this thing by the iota thing. So it's getting unnecessarily complicated. We'll see. So okay, that actually makes sense. Sure. So it's something like negative 2 iota sine theta, okay, minus iota. So that iota is multiplied now, so just plus. So it's plus e power I psi minus theta. Okay, that thing upon 2 cosine theta minus e power I psi minus theta. This is the quantity. So what we want to show is, right, that it changes its sign curvature to basically the exact opposite. So we just want to process like negative 1. Is it negative 1? It doesn't feel like that. This should have been sine theta for it to actually make sense. It's not. I must have messed up something. What did I mess up? Oh, okay. Wait a second. So you gotta put an iota of that. Oh, okay. That's a dot product. So okay, that actually does not change anything. You still have the pi by 2, don't you? Yeah, you do. So frustrating. So tangent vector, what you want is the derivative of tangent vector is supposed to have done all that. And r dot. What the hell? Oh, wait a second. R1 is, well, that's also a unit tangent vector. We shouldn't worry about that. It's easy to see intuitively this is happening, but is it happening actually? Let's go sine theta, and then r double dot is like iota and all that. So it's supposed to be sine theta. Why didn't it work out that way? What if I have to multiply the iota before the thing? Well, if that was the case, then this would actually worked out. Sure. So was it supposed to be r double dot upon iota or something? This is frustrating. Just took a second derivative. What's the big deal with this? It's a dot product, so taking the second derivative shouldn't matter. It does matter somehow. The hell? This sine. If this was a cosine, it would be all okay. What the hell? Why did it be the way it is? These two are not equal. They're definitely not equal in any sense. Right? These two are also not negative of each other. The only way that would happen would be like if 2i sine theta would be equal to 2 cosine theta, which we know is possible. But wait, okay, wait. So you reflect it about any line, and then okay, changes the sign of its sine curvature. Oh, so it does not make it necessarily completely negative. It just changes the sign. So all we have to show is that this quantity is a negative quantity. I see. So it's clear for theta equal to pi by 4 this would happen. What about, so if I did this thing, so it's supposed to be psi dash, so it's negative psi dash, psi naught, and then you got this stuff, 2 sine theta, it's an iota actually, but whatever, so 2 iota sine theta. Heck, that's not gonna work. So just, what the heck, so e power I psi minus theta minus 2i sine theta upon e power I psi minus theta minus 2 cosine theta. Right, the sign of the quantity has to change. This firstly should be a real number. Is it a real number? Well, doesn't look like that. So minus 2 sine theta. What the, doesn't look like a real number at all. What if that was negative or something? No, it's not negative particularly. Now isn't this frustrating? Hey, so both of these were negative. How did I make that? Oh, because I multiplied by iota. I divided by iota, didn't I? Oh, if I divided by iota, this should be negative over here. Still, it doesn't really matter, because now it's just like, okay, so we just have, this is not there. What the, just multiply by negative on both sides. This is like just a positive. Okay, this may not even be a real number, but it has to be a real number, right? What am I even looking for? This is the arc length of that. It's reflected in a different way than what? So arc length changes. It's still a unit vector. Yeah, sure. Just some sort of quantity like this. And for pi by 4 it certainly changes. Yeah, changes the sign completely. We also know that any rotation change won't change anything because of the previous theorem that we had, that if you fix your curvature for the unit parameterization, in that case it doesn't matter how you rotate it or you translate it, like it will still have the same curvature, right? So if you can just reflect by 45 degrees, so then across the y equal to x line, your curvature sign changes. In fact, it just becomes the negative of what it was previously, and then you can just like rotate it, and yeah, what that would mean is the curvature will just be negative of what it was previously, because it's still the same thing. So okay, you don't have to do all of this messy algebra. In fact, the point is you just reflect about the y equal to x line, and then you rotate, and the curvature stays the same for the corresponding points. Yes, so we just care about the sign in any case, right? So this was actually easy to show, because either the curve has, so the curvature is like always, it's not always positive, is it? When is it negative? Curve would be negative when your dt by ds is, well, that's certainly possible to assume, sure. Yeah, I mean, it changes the sign, makes sense. Okay. 11th, it's like unit curvature, so just change that. I mean, okay, it actually stays the same, doesn't it? It just changes the sign. In fact, the corresponding point is not the reflected point, but rather, oh, I see. So you rotate that, then you reflect it. I get it. It's different. Okay, next question 11. So what I was saying is, so this is your origin, whatever curve you have, rotate about the y equal to x line. This is really bad, but yeah. And then you rotate this thing. How do you rotate this? I don't know, you can rotate this. So yeah, just rotate this or and translate at the same time, to get the rotation across some other line. So this was the rotation. So it's the reflection along some other line. You can just rotate and translate this curve, and that does not change your curvature function if it's a unit parameterization, and this just makes it negative. So okay, that's actually not so bad. Question number 11 was a different thing. So question 11 is, show that if two plane curves have the same non-zero curvature for all values of t, then gamma dot obtained from by applying a rigid motion or a reflection in a straight line followed by a rigid motion. Wait, what? A rigid motion, which is a rotation plus a translation, sure, or a reflection in a straight line followed by a rigid motion. So okay, that gives you sort of all the possible symmetries of gamma t. So they are saying they have the same non-zero curvature, so the same unsigned curvature essentially. I see. And oh, it's non-zero everywhere, which means it never crosses the 0 point, so it's either all positive or all negative, right? Okay, so we already had that theorem that rigid motions, like, do not change the curvature at all, right? The same point of t, huh? Right, so like gamma would be something over here, gamma, when we say curvature we mean with respect to s obviously. So it's like you rotate and translate this to get something like this maybe. So this corresponds to this point. So at t, this is gamma of t, and this is gamma of t dash, so gamma tilde of t, and so on. Sure. So that's a, yeah, that's a rotation plus a translation thing, a rigid motion. So that does not change the curvature. We already know that, right? We know that because for unit parameterization, this holds, and so we can reparameterize it and it still holds, because yeah. In fact, that wasn't even for unit. It was actually in general, I suppose. So that was that theorem, right? Yeah. Okay. So that if two plane curves have the same non-zero curvature, right, bar can be obtained by applying a rigid motion. So we already saw that you can do a reflection around the y equal to x line, right? And then you can rotate. So that's going to give you a reflection along any line or something like that. So yeah, your curvature just becomes negative, and then you can rotate it. Signed curvature becomes negative. The unsigned curvature is like staying the same. So that actually does it. Question 11 was easy. So the only real thing that we have to show is first that reflection around y equal to x inverts the curvature, and the other thing we wanted to show was, heck, what did we want to show? I kind of forgot that. Yeah, so we wanted to show that rotation plus translation, that does not change the curvature at all, which is okay actually. I mean, what is a rotation plus translation? It's just this stuff. You just add a complex number z0 or gamma naught, whatever you want. I just call it z0. Multiply by some complex number z1, unit complex number, so just basically e power I theta, and then your gamma of t, right? That's what your gamma tilde of t would be, right? But taking a derivative of this stuff, what is like gamma tilde dot t is equal to z0 plus e power I theta gamma dot t. This z0 actually cancels, sorry. So what does that mean? That means that if here you had psi as the angle that gamma dot makes, this would be making something like psi plus theta. So the derivative over here of psi and derivative over here, both would be the exact same thing. So no issues at all. So 11th was easy. Question number 12. Show that if two plane curves, so okay, that's 11. Show that this curve is planar, i.e. it lines in the plane. Yeah, sure. This shouldn't be hard. So there are two ways of doing this. One, I can just parameterize it as, actually I might just do this thing. Yeah. So you have gamma of t is equal to, I'm gonna use r. R is what I'm more familiar with. So r of t is equal to just t power negative 1 plus t comma t plus 1 comma t power negative 1 minus 1. Sure. So r dash of t, so r dot I should say, that's just so basically the velocity, that's equal to negative t power negative 2 plus 1 comma 1 comma minus t power negative 2. Your acceleration, which is r double dot of t, that's equal to, come on, so just 2t power negative 3 comma 0 comma 2t power negative 3. Right. So firstly, what's v cross a? That's something we have to be sure of. So that would be this negative t power negative 2 plus 1 1 minus t power negative 2, and you can just take this stuff outside, so 2t power negative 3, and then you got 1 0 1, which would be 2t power negative 3. So this is like this it's just 1 plus t power negative 2. For that it's negative, that is whatever, just this and that. So just negative t power negative 2 minus of that is like plus t power negative 2 minus 1, it's cancelled, it's minus 1, and yeah, that seems about right. And for the last one it's just this and that, so that's 0 already, so it's minus 1, right? Cool. So what do you see? You see that this guy's magnitude is never going to be equal to 0, which means your v cross a is always like non-zero. So what's the magnitude of v cross a? That would just be 2t negative 3. I'm assuming t is a positive quantity, I have no idea actually. Then you got the square root of all of this, like square root of 2 plus this thing squared, so it's like 3 plus 2t negative 2 plus t negative 4. Right. Okay, so that's the thing. Now next what we are looking for is like, so we also want the r triple dot essentially. That would just be negative 6 t power negative 2 comma 0 and negative 6 t power negative 2. Okay, so that's exactly the same thing as r double. What does that mean? That means that the determinant r dot r double dot r triple dot that is equal to 0, but then we know that the torsion is just equal to r dot r double dot r triple dot upon this stuff v cross a, but then the torsion is 0, and the torsion is 0, it means that this thing is planar because your b vector never really changes. So 12 was easy. Question number 13. Question number 13 is show, okay, so let gamma be the unit speed curve. It's a unit speed curve, so okay, cool, then t is something like plus minus of s plus minus of c, again it's just not plus minus, but like plus of c essentially. Okay, cool. So it's a unit speed curve, and assume that its curvature is non-zero for all t. Oh, that's amazing. So it's either all positive or all negative if its curvature is like continuous. Define a new curve delta as the derivative of gamma. Sure. Basically your tangent vector, which is a unit vector and all that. So that this is also regular, and that if s is an arc length of parameter delta, then ds by dt equal to gamma. Okay, cool. So s is an arc length. So what's ds by dt? It would be just the same thing as the magnitude of d by dt of delta of t, right? Because your d delta that has the same magnitude as ds, right? So what you want to show is that this stuff would just be equal to kappa, which is kind of obvious, don't you think? I mean, if I don't know. So this is kind of obvious, yeah. So you have a unit speed parameterization, your delta of t. I mean, delta is unit all the time. So, but then the normal vector would just be like the same thing. It's just the derivative of this. This is in fact just the. It's in the direction of the normal vector. So you just gotta, you know, right. How do you define kappa? Kappa is usually defined as you know, the magnitude of t dot upon v, right? In this case, that will be something as del dot. So delta dot upon velocity, magnitude of that exactly. That's just one. It's unit speed. So guess what? This was actually very easy. It is in fact correct. Next question. Question of 14. Question of 14 is. So you also want to find the curvature and torsion. I'm not going to do any of that. I just really don't want to. Okay, let's just do it. Let's just find the curvature and torsion. So the curvature we already figured out, right? It's not a sine curvature which you're going for in any case. So your curvature is just. Oh, so this is the curvature of gamma. We want the curvature of delta, right? Wait, so delta is unit magnitude. Oh, it's a circle, right? Wow. So just the radius of this thing. So the curvature kappa is just, well, that was not bad at all. It really depends if it's like going forward or going backward, but whatever. So the unsigned curvature is just going to be like the magnitude of delta of t. So let's just say delta of 0, right? And the torsion is going to be 0 because it's a planar curve. I mean, come on, it's constant, right? It's constant, like unit length, all that. How do I even prove this thing? So what if gamma actually had a bit of a torsion? Sure, it can. If its curvature is not 0, that doesn't actually say anything, right? Find a new curve. It's not a circle, but rather a sphere, it seems. Yeah, so your delta is in a sphere. That's one way to think about it. Gamma could really just be anything. The curvature is easy. Sure, the curvature for such a curve, so for delta, that's just going to be like the magnitude of the time derivative. Sure, this dash t. It's doing something weird, am I not? Yeah, I am. Supposed to be like double dash t. So the tangent. Okay, we have to figure that out. We first have to figure out what is t. T is just del dash of t, right? Normalized. This is really messed up. The second derivative. That's unit speed. So what does that mean? That just means that if it's a unit speed, that just means like that this thing is perpendicular to your del. That's all it really means. But this could be anything. So we don't know. It's upon the magnitude of del dash of t. Yeah, this really just could be anything. Okay. Now time to do t dash. So or t dot or whatever. It will just be like del double dash of t upon oof, things aren't making sense already. No, I don't know. Find the curvature and torsion of it. Could certainly be a sphere. It could be in a sphere. In that case, the how do I even know? How do I even know? This curvature is non-zero. Yeah, for all I know, it just could be that. I don't get it. All we know is just that the magnitude of del is 1. That's the only information that we really have. It's on a sphere. Sure. And it does not necessarily mean that curvature or torsion would be a constant quantity. Could be any arbitrary crazy thing. So what does this even mean? All we know is like the normal vector is, yeah, because it's going in one direction. So that just means like, yeah, the tangent to del or del dot is like perpendicular to del. That's the one thing we know. But torsion could just be anything. Like it does not really matter. So I don't know. I don't think we can figure that out. So I'm just gonna move on. Really, they should be giving me options so that at least I can figure out what I have to figure out. Like in what form do I have to answer? In any case, a regular curve with curvature something is called a general helix if its tangent vector makes an angle theta with the fixed unit vector a. Tangent vector makes okay, cool, makes sense. Okay. Determine the relation between the torsion and curvature of fixed. So it's making a fixed angle with a plane as the same as if making a fixed angle with the axis. Sure. So its axis is along A, right? The relation between torsion and curvature of gamma. Conversely, show that if torsion and curvature of particular curve are related by T, okay, then the curve is a general helix. Okay, cool. Curvature is also same. So let's just prove the first direction, like that if it is a helix, then you have stuff happening. If it is a helix, then curvature, the sine curvature at least, sorry, the yeah, the sine curvature obviously. That's actually pretty easy to find, right? Yeah. I mean, locally, what's happening? That's the question. So it's just defined to be. So you can just do a unit parameterization most likely. Tangent vector was against. Sure, it just do a unit parameterization. So it just becomes like dt by ds. T is just yeah. So it's just t double dot. So it's just sorry, it's just gamma double dot. Right. Okay. And it's like perpendicular to that or something. Some weird thing going on. T by ds. It's just along the normal vector. Whatever. That's kappa. And the torsion will be something like gamma dot, gamma double dot, gamma triple dot. This is very messed up. On the magnitude of gamma dot, gamma double dot. Yeah, that's the thing. So first we have to figure out what this stuff is. Gamma dot, gamma double dot. So gamma dot is just a unit vector. Gamma double dot is it's the curvature. Okay, so it's a This is really bad. This tangent vector makes a fixed angle theta with the fixed unit vector. Okay, so let's just say A is your axis, as in A is this unit vector. The perpendicular distance from this axis is your point R, like to the point R. So just call that thing as capital R vector. This is R in the origin. So your this is your axis over there. So now this makes some sort of an angle with it for sure. Okay, always the same angle now. Stupid. Might not even be the case like that. General helix. It's not the same thing as a helix. It's some sort of a regular curve. In fact, it doesn't really matter. This is your torsion. How do you figure out this quantity? If your gamma dot always makes a fixed angle, what can you say? The only thing that we can really say is that the dot product of gamma dot with that A vector, so the gamma dot dot A, that's the same thing as cosine theta times these guys' magnitude, so just magnitude of gamma dot and the magnitude of A. So let's just say that A is a unit vector, so this happens. Sure, that's one thing. So taking a derivative of this thing, we might be able to get some stuff, like some really nice stuff. Interesting. Okay, so if I just set this to be a unit vector, then it just becomes like gamma dot dot A is like cosine theta, right? Taking a derivative on both sides, you just have like gamma dot double dot dot A is equal to 0, and obviously like gamma triple dot A equal to 0. So okay, I see. We know that gamma dot, gamma double dot, and gamma triple dot, they form a basis. So what I'm thinking is, if in the A component, so these two are not in the A component, what that means, and so they form a plane obviously, what that kind of means is, so either both of these are like dependent on each other, and if they're not, then you just have like A is equal to gamma double dot cross gamma triple dot upon the magnitude, something like that. I see. Right, so essentially this whole thing you can just rewrite as just having an A over there. It doesn't really matter because you can kill out everything else, right? And so this times of cosine theta obviously. That's interesting. So it's tau equal to lambda k. Between the torsion and the curvature of gamma double dot and gamma triple dot. You can do some sort of an orthogonalization. Not helpful. It's not helpful. So velocity and acceleration, sure. Something across A, so it's cosine theta times A, sure. And then plus the other stuff. So A is for, okay, the collinear stuff is just the thing we shouldn't really care about. I see. So what you can do is just say that. Mm-hmm. I see. So gamma dot would just be like, so these two are not going to be the thing. It's a cross between that in any case. So the stuff is perpendicular. Think about it. How do I go up? And then orthogonalize the whole thing. Gamma double dot, gamma triple dot. Think. Oh, I can use this fact. So if gamma dot and gamma, right, if gamma dot is a unit vector, in that case gamma double dot would be perpendicular to gamma dot. Interesting. So then that means gamma triple dot, yeah. It's perpendicular to that, huh? Interesting. In that case, I can just take the magnitudes directly. Isn't that right? Interesting. Okay, so gamma dot is something like that. Gamma double dot is something like this. Gamma triple dot would be, I actually don't know. It could be anything really. I just put it as some vector like this, right? And A is something that is, it could actually even be having, not sure. So A might be a vector like that. So in fact, the better thing to do would be like to put it. It has to be perpendicular to that, huh? So A and gamma dot both are perpendicular, so this would be the thing. So both would be perpendicular to gamma double dot, right? Okay, and then gamma triple dot is just somewhere, some random vector, we don't know. Yeah, sure. We also know that, okay, so this is actually perpendicular. Oh, so gamma triple dot is also perpendicular to A. Gamma triple dot is not necessarily perpendicular to gamma double dot, is it? No, it's not. And both of these are in the plane which is perpendicular to A, and A is in the plane which is perpendicular to gamma double dot. What is even going on? So it's a constant theta, right? It's a constant angle theta at all times. Hey, at all times, that's interesting. We know that A is perpendicular to gamma double dot, so it can only be in the plane like this. Interesting. That's just geometry, it seems. So gamma double dot is in some direction. Gamma dot, let's say in this direction. This is your plane perpendicular to gamma double dot. Let's say that theta is this angle, and so this is your A vector or unit vector, whatever. Gamma triple dot should be something like, then like it's making 90 degree with this. That's a possible scenario, or this might be a possible scenario. These are the only possibilities, right? So then we want we want this triple product, right? So A gamma double dot and then this stuff. So right, yeah, so just the parallel pipette. So what this would just be like, so A is a magnitude in any case, so it's like 1 and then the magnitude of gamma double dot, and then so this is going to be like, the height is where we go for. So this angle is theta, this is 90 degree, so this would be like theta minus pi by 2. So the sine of that, which is cosine, we just want a magnitude in any case, so cosine of that is cosine of theta. Yes, the sign of that is like this, so or the negative of that, I suppose, and then the magnitude of triple dot. So you're getting something like negative cosine square theta, and then you got gamma triple dot upon gamma dot, since that is weird. Okay, fine. So that's the torsion. Curvature is just that. How does gamma triple dot work into all of this? Something isn't right about this, isn't it? Yeah. Mm, but that has to be gamma triple dot, right? That's the way we define torsion. It's so frustrating. Hey, wait a second. This angle is theta minus pi by 2. This angle is it's 90 degrees, right? Because it's perpendicular to A. Oh wait, if it's perpendicular to A, and gamma is also perpendicular to A, but it's not necessarily perpendicular to gamma double dot, is it? No, it's not. This is not working out. Gamma double dot is certainly not perpendicular to that. Not helping, not helping. What the hell? No. No, this does not make sense. Mm. I must think about it. This is the cross product. Since it's a unit vector, we can just write it like this. These are just perpendicular in any case. Then this is what we're looking for: gamma dot, gamma double dot, gamma triple dot. We know that that the magnitude of gamma dot doesn't change. So gamma dot square, the derivative of that, so d by, so that's just equal to 1 all the time. So taking a derivative of that, what you would get something like gamma double dot, gamma dot, yeah, so just 2 of that is equal to 0. Sure, this is equal to 0, so it's perpendicular to this thing. But taking another derivative, you just get like gamma triple dot plus gamma double dot squared, that's equal to 0. So the dot product between gamma triple dot and gamma dot, that would just be like negative the magnitude of gamma double dot square. Sure. So if I had to think about it, this is gamma dot, this thing is gamma double dot, like perpendicular basically, and then the gamma triple dot is like somewhere floating in space. So the dot product of that is gamma dot. You have figured that out. If you remove that, then this is the part which is perpendicular to gamma dot, right? This is bullshit. This is complete bullshit, isn't it? The dot product doesn't really help. We want dot product with comma dot cross comma double dot, not the. Okay, what else do you know? You know that A is perpendicular to both of these guys. That's making angle theta. If I use A as this thing, it's perpendicular to both comma double dot and comma triple dot. Same time there is gamma dot and okay, gamma dot may not even be like that. It's just something perpendicular to both of these. I just without associativity say this thing is like gamma double dot. Now gamma dot has to be perpendicular to this, so it's in this plane. Yes. So gamma triple dot might be something like that, and this might be your gamma dot, right? And so this would be theta. Sure. Okay, then what? So what we want is the parallel pipette that is made by this. So this has to be 90 degree. Okay, there is actually already 90 degree, and yeah. The angle that would make. It's not getting us anywhere. So we can just think about the part of gamma double dot, which is so triple dot, which is perpendicular to A, because any part that is collinear to A will be cancelled out in any case. Sure. How is this even helpful? It isn't helpful. That's the problem. I want to find a relation like that, huh? Without knowing what the actual value of gamma triple dot is, it's just almost impossible, isn't it? So you know gamma triple dot gamma dot, yes. You know gamma triple dot A, yes. You do not know gamma triple dot gamma double dot. That's a problem. Wait, so that means you also know the thing like gamma triple dot whatever this quantity is. So both of these are just unit vectors. Yeah. So you subtract that, you might be able to get that quantity. Right. Perpendicular to that. Sure. Certainly not perpendicular to that. This isn't getting us anywhere. Okay, let's define this as the B vector, right? Okay, so since it's making angle theta, right, what you can say is gamma dot is just equal to so yeah, it's just going to be like A cosine theta plus B sine theta, because it's already perpendicular to this thing, so just B A at B sine theta, like that. Sure. What about gamma double? Okay, we don't know about this thing. You also know that gamma dot dot gamma triple dot, that's equal to negative of this thing squared. That's one thing we know. Taking a dot product with that, what would you actually get? You just get something like gamma triple dot. What else do you know? You know that also gamma triple dot dot this thing is 0 in any case. So gamma triple dot dot b. Interesting. Hey, I've seen this before, have I not? Gamma triple dot dot b. Oh wait, what is this stuff? B is okay. So this is along the normal vector. This is along the tangent vector, and so B was defined to be t cross n, right? This is a unit in any case, so that's not gonna matter. So T is essentially just gamma dot, but n is slightly more complicated. So oh, I see. So B would be just gamma dot cross gamma double dot, but this upon the magnitude of gamma double dot, right? So interesting. So this is actually what we're looking for. But yeah, so taking a dot product, what you get is like this sine theta, that is equal to negative of gamma double dot square. Hey, that's actually very nice, because yeah, so then you can substitute that inside and just get like the triple product, gamma dot gamma double dot gamma triple dot sine theta upon the norm of this thing, that's equal to negative squared. Sure, so this becomes cube, and then you just gotta divide by the same thing. So okay, so it's just like this thing squared. Sure. So basically it just becomes negative squared upon sine theta. Yeah, that's the idea. So what did we just get from all of this? What we got was that torsion is this quantity, negative magnitude of gamma double dot squared upon sine theta. What is kappa? Kappa is just it's just this thing, right? It's just gamma double dot's magnitude, right? Am I missing something? Oh, sorry. So this thing is right. It's supposed to be square actually. It's this thing squared. So you would just have this thing squared, this thing squared. Sure. So yeah, you got this. You actually have to multiply this by square again. So this just becomes one single one. Right. So kappa is just this, which means like tau equal to negative kappa upon sine theta. Right. I see. So our lambda is just like negative 1 upon sine theta, it seems. Right. So for 14, you just have tau thing equal to negative sine theta, sorry, negative cosec theta, kappa. Yeah. Now the other question would be that what happens if you know uh, if these are related like this thing. So if tau equal to lambda kappa, if that happens, then we want to show that the curve is in fact a general helix, right? Okay. I mean, only if you can write lambda equal to negative cosec theta somehow. If that's possible, then this is also possible. I feel this is not supposed to be cosec theta, but rather something else. But yeah, it probably is. That is the unit binary in any case. So just what the hell? kappa is just d tau. dt by d is the magnitude of that, which is just the gamma double dot thing, right? Yeah. Never mind all that. So anyway, we want to show this thing. So basically just got so these will be perpendicular in any case. So I'm just going to say gamma double dot squared. Kappa is just this. So what you're saying is something like this. Okay, amazing. So we know that, okay, so basically only the part of gamma triple dot which is, you know, not in gamma dot or gamma double dot is the one which we are essentially looking for, right? The magnitude of that. Oh, so this shouldn't be so hard to extract. Basically what you're saying is something like gamma double dot. So just finding a projection on this, isn't that right? Yeah. So that minus the projection, so it's just like gamma double dot dotted with gamma dot, and then gamma dot upon the magnitude. So just magnitude of gamma dot squared, which is 1, right? Minus triple dot dot gamma double dot 1 magnitude squared. That thing is the reduced thing. So this guy's magnitude, that has to be equal to, you know, lambda squared. Sure. Now what can we do about this? Well, the first thing is that gamma triple dot dot gamma dot, it's just the negative of gamma double dot squared thing, right? So you can just replace that by that. So it just becomes plus. Okay, that's one thing. Sure. This is very weird, actually. It's always just that. How do I go ahead from this? No, this isn't actually helping. Nope, no idea. How is this actually working? This isn't fun. This just isn't fun at all. What do I do? What do I do? How does that prove that tau equal to lambda kappa? Tau is this quantity. Okay. I mean, okay, so if tau equal to lambda kappa, how does that prove it's at a fixed angle with some unit vector? I can't even backtrack my whole thing. Can I? No. I just move on. Like, let's do it later. This is like it's not clicking for me right now. So second pending. Let's go to question 15 instead. Question 15 is find b and tau for the space curve. So b is, I suppose, just the, yeah, it's just the t cross n thing. So this is just normal calculation. So r is given. Sure. R is e power t cosine t. So just basically the complex numbers. But and anyway, just do the thing. So e power t cosine t, comma e power t sine t, comma 2. So what's r dash? Sorry, r dot. R dot is just take a derivative of that. Huh? So it's e power t cosine minus sine, comma e power t sine plus cosine, comma 0. R double dot, that would just be minus sine plus cosine, cosine minus sine plus cosine. So it's not plus, it's minus. It's just minus 2 sine. So minus 2 sine e power t, comma sine plus cosine minus sine. So it's plus 2 cosine. Yeah. It's very familiar somehow. So this just turns out to be s plus c, right? So just minus 2 e power t s plus c, and this would just be cosine turns out to be this stuff. So just 2 e power t c minus s 0. Sure. So the torsion isn't so hard to figure out. The b vector, you can figure that out as r dot dotted with r double dot, right? No, you have to first figure out the tangent vector. So p would just be like normalizing this stuff, which is like what's c squared. It's like, and add that, so it's minus minus cancel. It's like it's already a constant vector apparently. Oh no, but there's an e power t stuff going on. So okay, so it's just c minus s comma s plus c, that thing upon square root of 2. So your normal is just be like, so t dot firstly. So this t dot is like derivative of this stuff. It's like 1 upon square root of 2 minus sine plus cosine, minus cosine, sorry, comma, what is this stuff? Just cosine minus sine. And so it turns out this is okay, this is fine. It's already a unit vector at this point. So that's basically just our n. So you just gotta take a cross product to get b. And then you can use the formula to get the other thing. Yeah, right. So it was something like Tn and then dn by ds, which is like n dot by v essentially. So the magnitude of this v thing is just e power t square root of 2. So if I were to do that, n dot would just be it's all unit vectors like so far. Okay, n dot is a unit vector. Your b is, wow, this is not going good. It's supposed to be dn by ds. I'm really losing track of this. Yeah, I really am losing track of all of this. Anyway, so just figure out what b vector is. That will like help, because you can just directly figure out the dv by dt thing at that point, right? So once again, your tau is just like your b dot n. So once you figure out your b thing, it's okay. So b is just n cross, so t cross n. What the hell, man? So you can just forget the k thing completely. Okay, so as for I, it's just like 0 0. For j, it's also 0 0, so it doesn't matter. It's like 1 by 2, 0 comma 0. And then for the k thing, it's t cross n, right? So just this and that. Yes, so it's c minus s squared, which is c squared minus 2sc plus s squared, minus this. So that's actually plus, so just plus all of that, which should just be 2. So it's just gonna be like 1. Whoa, that is very weird, because now it's like a constant. It's very much weird, but actually that kind of makes sense. I mean, Yeah, yeah. So unit vectors cross product k hat is where it is. Sure. So what we wanted to find out was like b dot is just 0 in any case, so your torsion is actually 0. So tau is 0 and you got the b. So b is 0, 0, 1 and your torsion is 0. Okay, what about b? B is, let r of t be equal to this. Once again, just the same stuff. So your r dot is sine h of t comma minus cosine h of t cos t comma 1, right? So your tangent vector is like what? Oh, I see. So sine square plus cosine square, that's so sine h square plus cosine h square. Ooh, not very good. But you gotta do it, huh? And plus 1 over there. Interesting. Wait, what cosine h square plus 1? So sine h square plus 1, that's cosine square, so cosine h square. So it's just 2 cosine h square. So it's like 1 by square root of 2 cosine h. By the way, cosine h is like a positive quantity, so it's completely fine to be doing this. It's 1 upon that. So sine h of t, cosine h of t, and then 1. Sure. So what's your n? I bet you can actually sort of simplify this whole thing, but yeah, just try to do it directly. So first you just want to figure out what t dot is. So t dot is, oh, it's gonna hurt. It's gonna really hurt. It's minus 1 upon square root of 2 cosine h squared t, and then on the top you just got sine h of t, and all of this stuff, sine h of t, cosine h of t, 1, and then plus 1 upon square root of 2 cosine h of t. So I'm gonna say it's like cosine h squared t cosine h t, and then you got just cosine h t sine h t 0. So sine square of h t negative, cosine square of h t, what's that? That's just gonna be 1. So it's like 1 upon square root of 2 cosine h squared t. This thing is just 1. Now, oh, this just cancels. This is 0, 0, not 0. That's a 0 over there. This thing is minus sine h t. Yeah, that's just how it is. Okay, so you got your t dot. You will try to normalize that, and in normalizing we'll just have like cosine h of t in any case. So it's basically just 1, 0 minus sine h of t upon cosine h of t. So you got these two. Now just gonna take cross product, and that's gonna give you a b. Oh, this is some messed up stuff. So it's just 1 upon square root of 2 cosine h squared t, and then the cross product between t. So I'm gonna use sc and 1, although I usually use it for sine cosine, but I mean it's kind of similar over here. This stuff turns out to be like what? It's, so that is like negative sc plus 1. No, that's 0. It doesn't really matter. For this one is like this and that. So it's minus s squared and then 1. What's 1 minus 1 plus s squared is okay, but oh, it's negative 1. Sure. Sorry. It's 1 plus s squared. So it's just actually cosine. Cosine h squared. Okay. And for this one it's minus cosine h. Yes. So it's this stuff. So you can take one of the cosine h out, because these are always positive in any case, and say it's going to be negative sine h of t comma cosine h of t comma minus 1. Interesting. Yeah, it makes sense, and it's perpendicular to these things. Sure, I mean it's okay. So that's your b. You're gonna take a dv by dt thing, which it's not gonna go away, man. Right? Yeah. But let's just do it. So dv by dt is 1 upon, oh no, oh no, oh ho ho ho, this is not going good. uh, this is, by the way, not your t dot, this is supposed to be your n. Sorry for that. Okay, well, we don't really need the t thing anymore, so just this. Okay, what's dv by dt? So it's going to be negative sine h of t upon square root of 2 cosine h squared of t, and then all of that I'm gonna write as minus s c minus 1. I think I've seen this before, I don't know. Plus 1 upon square root of 2 c squared c, and then that's like minus c is 0. Let's try to match stuff up. So it's minus cosine h squared and then plus sine h squared, which is just exactly minus 1. So it's minus 1 comma, that cancels just like before, and this leaves us with sine h of t. Right, that's dv by dt. Which, no wonder, is actually a long minus n. So it's minus n times 1 upon 2 cosine h of t. So your tau is just 1 upon 2 cosine h of t. Yeah. Okay, cool. Which is basically like what, 1 upon e power t plus e power negative t. So that was done. Next question is, so we've got 2 more questions to go. Question 16 is, a frictionless particle starting from rest at time equal to 0 at a point a comma 0 comma 0 slides down the helix under the influence of gravity, as in the accompanying figure. The theta in this equation is the cylindrical coordinate theta, and the helix is the curve r equal to a, z equal to b theta. What is r? R equal to a, z equal to, oh okay, so it's r theta, cylindrical coordinates. Sure. We assume theta to be differentiable function t. Sure. The law of conservation of energy tells us that the particle speed after it has fallen straight down some distance is z, is just this stuff. Okay. Find the angular velocity d theta by dt when theta is equal to 2 pi. Oh, this shouldn't be hard to do actually. So you just want, yeah, so you know how to find speed at this point. So capital R is just given as, you know, r e power I theta plus z is just b theta, so b theta k hat. So your dr by dt is going to be like what? It's going to be something like e bar I theta, and then you got r dot plus I theta dot r stuff, and then plus you know, b theta dot k hat. Yeah. So the magnitude of this thing, that's just going to be the magnitude of this stuff, is like what? It's just square root of r dot squared plus theta dot squared r squared plus b theta dot squared, so like b squared theta dot squared. Sure. Okay, so this thing is going to be equal to square root of 2g z, where z is the amount of height it has fallen down, which we know is just b theta. So what does that mean? It just means like r dot squared plus theta dot r squared plus b squared theta dot squared, that's equal to 2g b theta. Alright, what do you want to find out? Find the angular velocity, so basically theta dot when theta equal to 2 pi. r is like a constant and it doesn't really change, so this would just be a. So what it's saying is like, wait, r dot is 0, isn't it? Sure. So we can actually rewrite this whole thing as just you know, theta dot times square root of a square plus b square. Yeah. Hey, that was actually much easier than what I thought. Interesting. So what you're saying is like that theta dot would just be equal to square root of 2gb theta upon, because that's the thing, right? Yeah, 2gb theta upon theta dot square root of a square plus b square. Yeah. So a is just that. So when theta equal to 2 pi, this becomes like theta dot is just this stuff, right? Just square root of 2gb theta dot, shit, it's not supposed to be theta dot, it's supposed to be theta, just not, yeah, so just upon square root of a square plus b square, right? That's just the speed, right? Yeah. Which is in this case, so it's just 2 pi, so it's like square root of 4 pi, so 4 pi gb upon a square plus b square. Amazing. That is part A. So to part B. Part B is express the particles theta and z coordinates as function of time. Functions of time. So first thing is like write the z coordinates as function of time, and then everything will fall into like the thing. So okay, z equal to b theta, or you could just do it directly, like, yeah, solve. So what you have is like theta dot is, so theta dot upon square root of theta, that's equal to all of this constant, so just square root of 2gb upon a square plus b square, right? And then yeah, just apply a 2 on both sides. It's like 2 over there. What does that mean? Well, sure, so like 1 by 2. Damn, what was I even going to do? Actually, you know what? Let it be. Just gonna integrate in any case. So, 0 negative 1 by 2 increments. 1 by 2 divided by that, just 2. So 2 square root of theta going from something to something. So theta equal to 0 initially, let's just suppose, to some theta, whatever, that's equal to I doubt it works like that, but well, yeah, I guess you can let theta be going from 0 to infinity. That kind of makes sense, right? Yeah. So we just have 2 square root of theta is equal to square root of 2gb. So take that 2 actually, just plug it in here. So just 2 a squared plus b squared, and then that's a t. Okay, that's awesome. So what do you have? You have theta is equal to gb upon 2 times of a squared plus b squared times t squared, and then z is obviously just b theta, right? So it's just basically going to be like gb squared upon 2a squared plus b squared t squared, right? Yeah. Just like so that it makes sense, these are of the same dimension, so that's a unitless thing. And then g is like meter per second square, t square is like second square, so this actually makes sense. Next thing to do, which is come on, just select everything. So the next thing is C, which is that express the tangential and normal components of the velocity and the acceleration as functions of time. I do not want to be doing all the calculation. Does the acceleration have any non-zero component in the direction of the binomial vector? So okay, r dot, r triple dot, all that. Okay. So I guess we already did the velocity, right? Yeah. The tangential normal component of velocity and the acceleration. What do you mean the tangential and normal component? I mean, something doesn't quite Look, dr by dt by definition is the tangential component. So this is weird. What are you even talking about? I don't know. So we know what dr by dt is. That's enough for me already. So dr by dt is just this stuff, e power I theta, right? And then d square r by dt square. It's just like another time derivative of this stuff. So just what? Oh, and by the way, r dot is like 0, so that is not there. And then now you know what theta dot is. So r is a, so just like I a theta dot is b theta times k. Sure. And then in another derivative, just have, like we just be having like minus e power I theta dot square plus iota e power I theta, oh god, theta double dot, yes, plus b theta dot k hat. Okay, now one could find the binomial vector by taking cross product. So I'm gonna write everything in this basis, e power I theta, I e power I theta, and k hat. So writing everything in that basis like gives me an advantage, since I can just do some very simple calculations. So this will just be like, oh by the way, you have to first normalize these two. Yeah, you would have to normalize this vector dr by dt, huh? Oh, so the good thing is like this actually, what's the magnitude of this stuff? It's like theta dot square plus something theta square. Yeah, so this is not like necessarily normalized in any case. Okay, I mean you have theta now, so it's all doable, I suppose. So this is dr. Let's just not do that right now. Actually, you know what? We will be needing in any case, so it's okay. I suppose when they said normal and tangential component, what they're kind of asking is like the component that is tangential to this surface, something like that. I have no idea what they're talking about. Sure, I'm just writing these as functions to me. Does the acceleration have any non-zero component in the direction of the binomial vector? So the acceleration is completely inward, right? A tangential vector is like that. So it's binomial vector is like this. Has any non-zero component in the direction of the binomial? No, it does not, right? Why would it? Look, it's just going through a circle, and like in the z direction, it's not changing at all. So in the z direction, the acceleration is 0. In the xy plane, it's going inwards, and yeah, so it shouldn't matter. Yeah, it does not. So c is just a 0. So no, basically, without even doing any calculations. So question number 17. Suppose a curve size 16 is replaced by the conical helix a theta whatever. Express the angular velocity as a function. Okay, it's the same exercise as before. So given r, given this stuff. So once again, your capital R is just r e power I theta. So it's like a theta times e power I theta plus b theta k hat. So your dr by dt. Right. Right, so what was the special thing about it? I don't know. But once again, it's the same thing, like square root of 2gz, that's the velocity at any point. So in any case, dr by dt is, yeah, I guess that should make sense. So dr by dt is, take the derivative of this stuff. So just a e power I theta plus b k hat plus, okay, this sense of theta dot plus a theta iota e power I theta theta dot. So this theta dot times stuff. What does that mean? The magnitude of this stuff, that's just theta dot square root of all of this. So it's like a square plus a square theta square plus b square, that's equal to square root of 2gz, which is like square root of 2gz, which is b theta. So it's that. Interesting. So what you have is like theta dot. Oh, this is not going good, is it? No, it's not. Oof. Squares, no, whatever. This is not something which like I want to be dealing with. Theta square. Can't I do something cool? I just dissolve the whole thing. No, I can't. It's the problem. I actually can't. Divide this by square root of theta. Sure, we'll do that. Yeah, that won't actually work out. You gotta do some sort of right, that's the only possible way. Is it? Not necessarily. Think. You will have to do some sort of trigonometry substitution, that's the only way. So this would be upon square root of theta and times square root of a square. So a square theta square plus, or just take the a square out. It just becomes like square root of theta square plus a square plus b square upon a square. Right. So we take the a out and it becomes the square root of 2gb upon a. Now you want to solve this equation somehow. Have I seen this before? I don't think I have. Anyway, try to think about it. So what you can do is like just say that theta will just be the square root of the stuff, so it's like square root of 1 plus b square by a square. This looks awfully familiar. It's just I don't know if I've seen this before. Anyway, the square root of 1 plus b square upon a square, right? What was I doing? Yeah, right, this times of tan psi or phi, let's use. Substitute that in, so what do you get is like square root of 1 plus b square upon a square. Okay, that times of secant square phi d phi, right? And then you just got this stuff, so like this squared in fact. And then you got just secant phi again, so just secant cube phi, and that upon this, so just the power of 1 by 4, yeah, to the power of 1 by 4, so it just becomes 3 by 4, and then just square root of tan theta. That didn't help at all. I've never seen this before. Yeah, never seen this before. I don't know how to solve this actually. That's a hard thing. Now what? Good question. Now what? This is like square root of s and then c cube. So the cosine on the top. So it's like c square and then you just got like sort of cosine over here. This is like 1 upon cosine square root of sine cosine. Interesting. Sine 2 theta is so sine 2 phi. Okay, it's one thing we can do. Minus cosine of 2 phi. How does that even help? That's the fun part, it doesn't help. Think about it. Can you somehow solve this? I don't know, I have not seen this one before. So I'll have to think about it. Okay, so I'll see you guys in the next video. Bye.